Hi everyone, I am Narendra Chaudhary, a PhD student at Virginia Tech, and I am going to present our self-supervised approach towards learning representations for knowledge graphs. We will first understand the problem and go over the present research in the area, and note the different challenges they face. Then present our solution hype and also look at the various experiments conducted to evaluate our model. Knowledge graphs are comprised of individual or group of entities connected by relations. This structure makes them suitable for several data storage scenarios. However, due to their large size, information retrieval through graph traversal, even with sorted ordering, is prohibitively expensive. Several knowledge graph datasets have close to 10 million nodes with trillions of relations between them. So, development of a method that could effectively perform logical queries over the knowledge graphs could greatly expand its application domains. An approach towards more efficient querying is to learn representations of the different entities and relations in a latent space, where algebraic operations could help us query the knowledge graph. For an example, in the product search domain, a model could learn to translate the product categories Nike, Adidas, and footwear to the latent space, and we can now use thresholds around them to query results from logical operations. One variation of this approach is query to box, where the authors aim to learn box representations for logical queries. As we can observe in the figure, this introduces a spatial parameter which is able to increase the precision compared to fixed thresholds over vectors. Query to box models each entity and relation as a hyperdimensional box and also define an intuitive approach to derive the projection, intersection, and union of the boxes. For example, projection is defined as the sum of the entity and relation, intersection is the overlapping space of two entities, and union is the overall space covered by the input entities. However, we note that this approach does not consider the inherent hierarchy present in knowledge graphs. For example, in product graphs, we notice different levels of hierarchy such as categories and brands. We notice such global or local hierarchies in other directed graph datasets too. For example, categorization of articles in Wikipedia or followers on Twitter, where an influential user would have more in-nodes than out-nodes. Thus, we find hyperbolic space to be more suitable for our model, which has in previous research been proven to be more effective on hierarchical datasets. To alleviate the challenges with previous approaches, we propose hyperboloid embeddings with a focus on solving the given challenges. We need the representations to improve querying over knowledge graphs, and the representations need to capture both hierarchical and spatial information. Also, we need to define logical operations such that we can use the geometries to learn our representations. Additionally, given the large scale of naturally collected knowledge graph datasets, we would prefer to develop a self-supervised approach and use unlabeled knowledge graphs towards learning representations. To model spatial enclosures, we model the queries as enclosures of two parallel hyperbolic segments or horocycles in a Poincaré ball. As we can observe in this figure, using an additional parameter to capture spatial information increases the precision of querying over knowledge graphs. Also, the final graph shows the distance between the entities at the same hierarchical level and entities at different hierarchical levels. We observe that distance between interlevel entities increases superlinearly in case of hyperbolic space. We also notice that leaf entities under the same parent get clustered together. This captures the real-world phenomenon where distance between entities at different hierarchical levels is supposed to be high and entities under the same parent are supposed to be close together. Next, we handle the popular query types of translation, intersection, and union. For translation, given the entity and relation hyperboloid, we define the projection query space as Mobius addition of entity and relation. For intersection, we return the overlapping space between the hyperboloids. And for union, we return the set. As given in the example, a translation query Nike would return all products associated with the brand Nike, and intersection between queries Nike and footwear would return all the results for query Nike footwear. Similarly, union is handled as the set of all its input spaces. Thus, a union over Nike footwear and Adidas footwear would return all products contained in Nike and Adidas footwear. Now let's look at representation learning from the queries. Different logical operations have different inputs and processing rules. We could use independent architectures to process each query type. However, this increases redundancy as we would need to learn different representations for each task and also figure out a way of integrating them. Thus, we add an operator signal that changes the network architecture according to the operation being handled. We start our model with random Euclidean boxes for all entities and relations, which we transform to the Poincare ball space. Additionally, there is also an input operator signal that defines the network structure for that iteration. According to this signal, the model processes the transformed embedding into a query space. In case of translation, it adds the head entity to a corresponding relation, or in case of intersection, it returns the overlapping space, or in union, it returns the set of all hyperboloids. Next, we calculate the distance of all positive samples and negative samples from the query space. This is done with a hyperbolic version of L1 now. We calculate two distances for each entity, one from the center and another from the limit of the hyperboloid. These are combined with a fixed factor. The objective of our model is to learn representations such that the positive samples move into the hyperboloid and negative samples move outside the hyperboloid. Next, we backpropagate through the loss to update our entity and relation embeddings. However, if we want to encompass and process the entire knowledge graph, we cannot depend on manually labeled ground truth. This is our motivation towards developing strategies that do not rely on manual annotations. So, we utilize the entities and relations in the training knowledge graph to make pseudo queries. For example, in the figure, this entity has two parents, and thus we model it as an intersection of two parent entities. This resolves our dependence on explicit annotation, and we can now learn representations in a self-supervised manner. Let's now move on to the evaluation of hype. Our evaluation focuses on the given 5 research questions. For the task of reasoning over knowledge graphs, we want to find out if hyperboloid embeddings perform better than the baselines at learning hierarchical relations. We also want to find the contribution of individual components in the hype model through an ablation study. We also want to find out if the representations capture relevant data features for a downstream task such as anomaly detection. Can hyperboloid embeddings also leverage auxiliary semantic information from the entities? And also, can we comprehend the latent representation space obtained by the proposed hype model? To answer the first question, we consider the query types of translation, intersection, and union. In translation, we use 1T, 2T, 3T, which respectively return the children, grandchildren, and great-grandchildren of an entity. They are also popularly known as multi-hop operations. For intersection, we check intersection of 2 and 3 entities and also how they work in congruence with a translation operation. For unions, we consider the union of 2 items and it's working in congruence with the translation operation. For example, a 1T query Nike would return all products under the brand Nike. An intersection query Nike shoes will return all products under the brand Nike and also under the subcategory shoes. A union between Nike and Adidas would return all products under the brand Nike or Adidas. A union translation query, Nike and Adidas shoes, would return all products under the brand Nike or Adidas and also all under the subcategory shoes. We consider the public benchmark datasets of Freebase, NEL, DBpedia, and also a proprietary subset of an e-commerce product graph. The primary baseline we compare against is query to box, and the evaluation metrics are the standard retrieval metrics of hit set 3, which is the number of correct answers in the first 3 results, and MRR, to additionally evaluate the rank given to the result. In our experiments, we find that hyperboloid embeddings quantitatively shows better performance than box embeddings across all query types and datasets, which provides evidence for the potential of hyperbolic space in querying knowledge graphs. To check the improvement from simultaneously learning from different query types, we compare our model against variations trained only on translation queries. We observe that training without complex queries reduces the performance both in terms of HITSIT3 and MRR. Additionally, we also check different methods for aggregation and intersection. The proposed model uses attention, but we test out deep sets aggregation and also vanilla averaging. We notice that aggregation through attention performs the best, and hence that is the one applied in our final implementation. We also check if trainable curvature for the Poincare ball aids our performance, and it does, but we conclude that the additional number of parameters does not justify the nominal gain, and hence we just use a fixed curvature set at the traditional radius of 1. Given that our goal was to learn our representations in a self-supervised manner, such that it also transfers to additional tasks, we evaluated hype on anomaly detection. We used precision, recall, and F1 score as our evaluation metrics. The primary objective in this experiment is, given a parent entity and a candidate entity, can the models predict if the candidate entity is a child or not? For this, we consider different levels of parents too. That is, we would like to check not only the parent-child relation but also the grandparent-child and great-grandparent-child relation. From the experiments, we observe that our model performs better in the evaluation metrics. Additionally, we notice that performance improvement is greater when considering parents at higher level, which is additional evidence of better performance of hyperbolic space in a hierarchical setting. In our experiments, we considered entities and relations as independent tokens. However, for this specific task, we also see that semantic information they contain can further improve our performance on the task of anomaly detection. So we tried to analyze if our model could also leverage semantic information. We learned semantic vectors from the product titles in our e-commerce product graph and concatenated them to the hierarchical hyperbolic embeddings, referred to in the table as HypeSC. The table shows some qualitative examples where HypeSC performs better than non-semantic implementation Hype. In addition to this, to comprehend the embeddings in the actual Poincare space, we provide visualizations of subgraphs from our dataset. As we can see, leaf entities are clustered together, whereas intermediate nodes are farther from each other, which very closely follows the real-world structure. In our paper, we empirically show that hyperbolic spaces are better at capturing hierarchical information and can be learned in a self-supervised manner from product networks. The ablation study shows the clear importance of using relatively complex queries such as intersection and union in enhancing Hype's performance. Hype's representation in congruence with or without additional information such as semantics can also be used for downstream tasks. The hyperboloids can also be visualized in a Poincare ball for better human comprehension. Thanks a lot for your attention. I am here to answer any questions. For any additional clarifications, you can also mail me on the given ID.